So, ResNet or residual network, the architecture that changed deep learning. So, it's one of the most important ideas in deep learning. Residual connection or escape connections. ResNet solved a major problem that prevented neural networks from becoming very deep. So, why deep networks had the problem? So we may think that more layers, more learning, and better accuracy. But researchers discovered something strange. Small networks work well, medium networks work better, and very deep networks often perform worse. There were two major reasons. The problem one is vanishing gradients. During backpropagation, gradients travel backward from the loss toward the early layers. So and each layer contributes a derivative. So many derivatives are less than 1. Example, we multiply the 0.5 multiple times, and if it's keep multiplying like 0.5 raised to the 20th power, then the gradient becomes almost 0. So the result, early layers receive tiny updates, early layers learn very slowly, sometimes they stop learning entirely. So this is called the vanishing gradient problem. Next is the ResNet's brilliant idea. So instead of doing the f of x, so the ResNet adds the value of x, where x is original input and f of x is learned transformation and y is output. This extra x is called residual connection or skip connection. So the input skips over some layers and get added back later. So the residual block is, so we have the code that concepts looks like if like initialize the identity x, we have the convolutional 1 and convolutional 2 for out. So the out, so we have the out is equivalent to out plus identity. That's it. The famous innovation literally out plus equals x. So the output plus equals x. So such a small line of code changed deep learning forever. So why does adding x help? So without ResNet, we only have the y value is equal to f of x, and the gradient is f prime x. Okay, so with ResNet, we have fx plus x, so the derivative f prime x plus 1. So notice the plus 1, that plus creates the direct path for gradients. So even if the f of x or f prime x is approximately 0, the gradient still contains 0 plus 1. It's equivalent to 1. So the gradient can continue flowing backward. So if fx becomes very small or vanishes, then the preserved x can take over. So imagine if we have the f of x equivalent to 0 and then y equivalent to x, so the block still passes useful information. So the network never completely loses the original signal. Next is ResNet learns corrections instead of replacements. So normal network output is fx, and the layer must learn everything from scratch. So we could think of the ResNet as output is equivalent to original information plus a small improvement. So each residual block only needs to learn what small adjustment should they make instead of what should the entire output be. So this makes learning much easier. So earlier features never disappear. This is one of the biggest insights. Suppose an early layer detects edges, a later layers detects corners, and even later layers detects eyes. And in the traditional network, those early edge features can gradually fade. So in ResNet, we have the edges, corners, and the eyes, while the original information keeps being passed forward through skip connections. So later layers can still be useful as earlier features. So what is downsampling? We saw the code in the laboratory, like if self that is downsample, that and identity is equivalent to self that downsample, and this argument is x. Why? Because addition requires matching shapes. We cannot add the dimensions that didn't match. So the downsample layer adjusts the identity path. Why ResNet was revolutionary? So before ResNet, we only have 20 to 20 to 30 layers was already difficult. Training error often increased when adding more layers. Regens is vanished. So after ResNet 50 layers trained successfully, 101 layers trained successfully, or even 152 layers trained successfully. This showed that very deep networks were possible, which influenced many layer or later architectures. So a reminder that fx is learn improvement and x is preserve information, so the output will be original information plus improvement.